Now, continuing to look at these graphs, slope is rise over run. We already know that. Well, if it's rise over run, then we have d over t. d over t is velocity, right, from that equation. So that means the slope of this graph actually represents your speed that you are moving, or the speed of the car that was going. So for this one, for A, our speed is 0. B, this looks like a pretty slow speed. C is a much faster speed. D, our speed is moving in the opposite direction. Because the line is straight, it is moving at a constant speed in the opposite direction. So it's getting closer to the sensor, closer to 0. For E, our velocity is changing. So there's a lot happening with part E. Our velocity is changing, which is called acceleration. We'll deal with that later. Quickly. The Doppler effect. Alright, so the Doppler effect is the apparent change in frequency for an observer that's relative to a moving object.
In the frequency of a wave caused by relative motion between the source of the wave and the observer.
The Doppler effect is perhaps best explained visually. So here's a thing that is emitting waves. It could be a fire truck emitting sound, it could be a star emitting light, it could be a duck creating ripples on a pond. Those are all waves, and they all look something like this. We see the Doppler effect happening when the thing that is emitting waves moves. In the direction it's moving, the wavefronts bunch up, and behind it, they spread out. If our object is moving towards a stationary observer, these bunched up waves are observed at a high frequency, and if the object is moving away from a stationary observer, the waves are observed at a lower frequency. So that is the Doppler effect, the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer. It makes sense, but it gets interesting when you consider some of its applications. So let's say you are standing in the middle of a road. That's you, and a car drives past you very fast. As it does so, it honks its horn, because you're standing in the middle of the road. The horn to you might sound something like this. So it starts at a high pitch and moves to a lower pitch, even though from the driver's perspective, the horn is playing the same pitch the entire time. So what's going on? As the vehicle's coming towards you, the sound waves that it's emitting bunch up, and so are delivered to you at a higher frequency, which you interpret as a higher pitch, because the frequency of sound waves is pitch. And then when the vehicle passes you and is moving away from you, the sound waves spread out, and so you hear them at a lower frequency, a lower pitch. So that's how the Doppler effect works with sound. It also affects another kind of wave, light. So let's say you look out your observatory and you see a star. Just like the car's sound waves, if the star is moving towards you, even just a little bit, the light waves that it emits will be bunched up, meaning that you see the light at a higher frequency than it actually is. Frequency in sound is pitch, so what does it mean for light? Well, if we look at our handy pocket electromagnetic spectrum chart, we'll see that a small change in frequency for visible light will change its color. Higher frequency light waves means bluer light, and lower frequency light waves means redder light. This is called redshift, and it may possibly be among the weirdest and coolest things of all time.
So we'll cover redshift in astronomy when you get there. But for physics, that's what we needed to know. So that's Doppler effect. All right, so now go back, revisit. What do you think now? Answer those 2 questions. And that's it. Make sure you and your partners have cleared everything up. And then you're going to work on your physics to go questions. And anything else? Ask me.